Friends, today we are going to start a new topic today, that is DC series motor. DC series motor, as the nomenclature is, it is in series. So we know there is a field winding and there is a armature winding. The field winding and the armature winding are supposed to be in series with each other. So and they must be perpendicular to each other. So now we have a supply voltage is V. The field winding is given with a resistance RSC. Armature winding is given with a resistance RA. The back EMF is given by EB. With a positive and negative sign. So this is what a DC series motor circuit diagram look like. So if we apply a KVL, the current through it, current through will be IA, and the field current will be same as IA, and armature current will be again as same. Right? So if I apply the KVL here, we can write here that E is equal to V minus IA RA minus IA RSC. So obviously I can make a shortcut this V minus IA RA plus RSC. Right, fine. So, and we know that E can be substituted with the term E is equal to some KB into phi into omega m. And also we can write torque in terms of KB phi into IA. So these two terms, what we can write now, we can in terms of E and T. That is, in DC series motor, this expression will change. This expression will change in DC series motor. How? Because the flux is no longer constant. Rather, the flux is proportional to or equal to some constant, let us say KE into IA. So if I substitute these values, then I can write E is equal to KB, KE, and IA omega m. And torque is equal to KB, KE, IA, this multiplied with IA, so IA square. So what I am going to get is a torque expression in this form and back EMF expression in this form. This is A back EMF. So we can write the back EMF as EB. So after getting this expression of EB and T, what we will do, we'll substitute this value of EB in this equation and try to see how the equation look like. So we can write here KB, KE, IA, omega m is equal to V minus IA, RA plus RSC. And here we can substitute, we can get what is the value of omega m is equal to V by KB, KE into IA and minus, so IA I will cancel, let us write, let me write, so RA plus RSC divided by KB, KE into IA get cancelled out. So final expression what we are going to get is omega m is equal to V by KB, KE multiplied by 1 by IA minus RA plus RSC divided by KB, KE. This is the expression what we are going to get. So, can we find out the top expression as well? So, in this expression, so simply put the value of the current here. So, we can write omega also, omega m is equals to V by KB, KE. Substitute the value of IA is here. So from here I will take the value of IA and substitute here, it will, the root over will come, and here we will get root over of T minus RA plus RSC divided by KB, KE. Because here is no variable, so we are going to get in this form. So in this two expression, one expression here speed depending on the torque, here one expression the speed depending on the current. So, lot of variables are over here. Let me try to simplify it. To simplify, we can write, let us say, this expression, the two expressions are there. Let us say this is this expression, let us say this is 1 and this is expression number 2. So expression 1 can be written as y is equal to, let us say, 1 by x minus c. C is a constant, and 1 is, you can say 1, or let us say d by x minus c. And expression 2 can be written as y1 is equal to d by root over of x minus c. So root over of a, let us say these two expressions are there. We can write like this, otherwise we can write y, and here instead of x, we are writing x, otherwise root over of some other value. So our objective is, if these two variables are there, they are inversely proportional, how does it look? And if they are inversely proportional with the same value of x, how does it look? So if x will vary in this direction and y will be here and y1 will be here, so how does it going to look at? So let us draw this one. So what we are going to get for y and x, we are going to get the curve somewhere look like this. This is the expression for y with respect to x. And another expression is y1 with x. So let us here draw with another pen here. So what we are going to get is, we are getting it like this, one another current. This is y1 with respect to x. So this is y1 with respect to x. The reason of showing you this simplified diagram is that both the y1 and y are inversely proportional to the x. Both are inversely proportional to x. So the curve will look like, when the value of x is high, y is low. When the value of y is high, x is low. So let us draw this in terms of the speed and torque. So if I will draw speed omega m, so there is, in the characteristics we can draw speed in terms of omega m with respect to the armature current, also in respect to torque. So let us try to draw both in a single diagram, if so that we can correlate between them. So speed with the current will look like somewhere here. Speed with the current, this is inversely proportional. So when we increase the load, the current increases and speed will decrease. And here at this point we can see that speed is high at a lower value of current. It is advisable that DC motor should not be started with a light load. DC motor should always be run with a loaded condition, right? And if we draw the torque characteristics, speed torque characteristics will be with speed. How does the torque vary? So like this, it will just vary in this form. So here the speed torque characteristics will be, this is the omega m versus torque, and here we can see that omega m versus current. Another characteristics that we can get from, we must know, is that how does the torque varies with the current. Usually the torque varies with the current means that expression is, T is, there are two expressions is there. One is, we know that T is equal to KB phi into IA. And another one is T is equal to KB, KE and IA square. So there is one expression where T is proportional to IA square. Here, if the flux is constant IA, so we were not going to use this. But the importance of writing here or this is that, let us see. If we are going to draw this one, so how the curve look like? So curve will look like somewhere, it's a parabola, so it should be like this. It should be like not like this. The curve will be somehow, it's a parabolic, so it will look like this. T is proportional to I square. But what happens in actual sense, the current is after beyond a certain value, if the current will increase, the flux will not increase. Flux will be constant. So in this term, flux will be constant beyond this new value. So if there are two lines, you can get a dotted line here. So what we are going to getting actual curve is, it will follow the parabola, then after some time it will join the main line. So this is what the actual speed torque curve will be, torque versus IA. The reason is, up to certain value, the effect of saturation will not come into picture. But after that, the effect of saturation will come into picture. Thus, we will get such type of curve. So these are what the DC series motor characteristics, and what is the difference from the other lectures here. Here we are mathematically proving what is the value of omega n with respect to T, omega n with respect to current, and try to draw the same figure. So this same figure the student read in the basic electrical, and in DC series motor, what in here we are reading is in the drive, that why this curve is because of this particular equation. So here we have chosen D as like in the 1. So actually it is V is some 220 volts. So KV, K is some value. So the D value will change, and C value will obviously very low value. So based on that, this curve will vary. So if the C value is like suppose 0.2 or 0.02 or D value is 1, then we are getting this such type of changes. If X varies, how does Y and Y1 varies? So with this, thank you very much.